Today we will look at several ways of turning on the high-power LED. Unlike general LEDs, high-power LEDs have a very large forward current. Thus, limiting current is a very important task for high-power LED applications. LED, or a light-emitting diode, is a semiconductor light source that emits light when current flows through it. Since LED is a diode, current flows in one direction, that is, when it is forward biased. To make the LED light up with sufficient brightness, the voltage must be applied above a certain value. This voltage is called the forward voltage. If a voltage higher than this is applied, the LED becomes forward biased and the light is turned on due to sufficient current flowing through it. The IV characteristic of the forward biased LED is shown in this figure. This figure shows the amount of current according to the voltage applied to the LED. In other words, when the voltage is small or reverse bias is applied, the LED does not illuminate, because current does not flow. Then, when the voltage is increased, the current starts to increase, and when the voltage exceeds a certain amount, that is, larger than the forward voltage, the current flowing through the LED increases rapidly. Therefore, it is important to limit the amount of current to prevent damaging the LEDs. The simplest way to control this forward current is to use a resistor. In the following circuit with an LED and resistor, the source voltage V should be greater than Vf, the forward voltage of LED for the current to flow. The amount of current flowing through the LED can be calculated by this formula: source voltage V subtracted by forward voltage Vf, divided by R. The resistance value should be selected, so that the amount of current flow doesn't exceed the forward current of the LED. The same formula can be applied to this circuit, configured in parallel. In the parallel configuration, the voltage applied to each LED is the same, so when a resistor is used for each branch, the previously reviewed formula can also be applied. Now let's see what happens when we use a common resistor for both branches. In this case, the resistance value should be reduced by half, if you want the same amount of current as before to flow through each branch. You should also note that the power consumed on the resistor is doubled, which can be a limitation for using this configuration. If the LEDs are connected in series, the voltage of the power source must be higher than the sum of the forward voltage of each LED. That is, 2 times Vf for this configuration. The current is calculated similarly as before, subtracting the forward voltage of each LEDs from the voltage of the power source, divided by R. This is the design guide for using resistors to limit the current. There are also some sites that gives you the calculation results similar to this page when using resistors. For high-power LED applications, the power rating requirement of a resistor can be impractically high, which is one limitation for using this approach. For outdoor applications, where the temperature can vary significantly, the maximum operating temperature should be taken into account. For more details on the specifications of a resistor, please refer to my video on how to select a resistor for your application. It is often necessary to mix the configuration. This page introduces an example of configuring the LED in a 3x3 configuration. As you can see from the result, the power consumption of the resistor is very large when you use one common resistor for each branch. This is showing the same configuration as before, but using 3 resistors for each branch, instead of 1. You can see that the power consumed by each of the resistor is significantly lower than before. Using a resistor is simple and intuitive, but the efficiency is low, due to the power consumed in resistors. And sometimes, it can be difficult to use resistors for high-power LED applications. One solution could be using a voltage regulator, such as these ones shown. The 2 modules on the right supports constant current as well as constant voltage, which could greatly facilitate LED circuit designs. The voltage regulators used in these modules are all step-down converters called LM2596. LM2596 doesn't inherently support constant current, but it supports constant current through the extra circuit added to the module. If you would like to learn more about the operating principle of this module, please refer to the video related to LM2596 in my video. Let's review the case of using a constant voltage-supported regulator. LEDs, like other diodes, have their own IV characteristic. Therefore, it is possible to light up the LED, if you adjust your regulator to output a voltage that matches the forward voltage of the LED. However, there are several problems using this method. First, is the forward voltage tolerance of the LED, which is generally known to have a tolerance of 20%. Therefore, even when the voltage of the regulator is kept constant at a value of V, the forward current will be different due to the tolerance of each LED. If the forward current is low, corresponding to the rightmost IV curve in the graph, the brightness will be low. And if the forward current is high, the brightness of the LED is high, but also has a possibility to be damaged. This is an example of the tolerance of an LED. To check the tolerance of the forward voltage, I measured the IV characteristic of 10 1-watt yellow LEDs. In most cases, 350 mA of current flowed at approximately 3.5 volts, but one LED had a same amount of current at about 3.25 volts. If a voltage of 3.5 volts was applied to this LED, the current flow would have been 500 mA or more, which may damage this LED. You can see that these 10 LEDs had a forward voltage tolerance of about 10% at a current of 350 mA. The second problem is a phenomenon called thermal runaway. When current flows through the LED temperature rises, and when the LED temperature rises, the forward voltage of the LED decreases. When the forward voltage of the LED decreases, the current flowing through the LED increases and the temperature rises further. This could damage the LED when this happens repeatedly. This is the result of an LED running from a constant voltage source. After initially setting the voltage so that the forward current flows about 330 mA, you can see that the current increases rapidly over time and flows up to 450 mA, which exceeds the nominal forward current requirement of 350 mA. The voltage drop is the result of the IR drop of the current measurement circuitry, so without those circuitry, the current can be higher than this measurement result. Due to these problems, it is very important to drive an LED with a constant current source. Using the CC/CV regulator as shown in the picture, you can set the voltage to VF and the current to IF to illuminate the LED. It is a typical and safe method, because the regulator limits the amount of current even for the problematic situation we have previously seen. When configuring LEDs in serial using a CC/CV regulator, we need to set the regulator voltage as the sum of the forward voltages of all the LEDs. Current can be set as the forward current of the LED. Therefore, the number of LEDs that can be connected in series is limited by the voltage of the regulator output. That is, the regulator voltage must be higher than the sum of the forward voltage of the LEDs. In parallel configuration, you can set the regulator voltage as the forward voltage of each LED, and the current as the sum of the forward currents of all LEDs. However, this constant current regulator itself does not provide current balancing for each of the branch. To overcome this problem, you can add a regulator for each of the branch, or add an extra circuitry, such as a current mirror with transistors. This example shows how to use a current mirror for mixed parallel and serial LED configuration. By using this method, current balancing can be performed on each of the branch. With some more circuitry, we can add a failsafe feature which protects the LEDs for several failure scenarios. I will introduce this method in detail on another video. The features of each method are shown in the table. Take a look at each feature when selecting a method that suits your needs. Coming up in the next video, I will introduce an LED driver, equipped with dimming function controlled by Arduino. Thank you for watching. See you in the next video.